Hey guys, so for today's video, I wanted to look a little bit more at graphs. Okay, now what makes graphs so great? Well, graphs show a lot of information at once, right? It can give you a lot of information about an object's position over a series of time, right? It can also give you a lot of information about specific positions or places that the object is at. All right, and so the nice thing is that we get everything all at once in a nice visual image. Whereas without this, we'd have to have a bunch of numbers in a table, or we'd just have to write out all the information. This gets a lot of information in one place at one time and makes it really, really visual for us. All right, now you may remember in our first unit, we worked a lot with distance versus time and velocity versus time graphs. So I'm going to review those really quickly, just to kind of remind us what we did there. But then I'm going to add in a couple of new graphs that are connected with some of the more recent things that we've been learning about. All right, so here we go. The first thing I want us to look at is to review these distance versus time graphs. Now remember that we could just read directly off there at any point in time at 3 seconds. This was my position. I can get that information really, really quickly and easily. The other thing I hope that you remember is that the slope here is valuable. Now remember that slope is equal to change in y over the change in x. So slope equals change in y over change in x. In this situation, y is the position or the displacement, and x is the time. And so that would be change in position over change in time. And your change in position, that's the distance that you've traveled, over the change in time, is equal to your speed or velocity. And so what we found out is that the slope of the distance versus time graph was our velocity. Okay, and I think you'll probably remember that. Remember, we were talking about how when it's flat, your position's staying the same, therefore your slope is 0, your velocity is 0. If the line is steeper, that means that you're going faster. That's because your slope is steeper, right? So we talked about a lot of ideas with that. Okay, we also looked at velocity versus time graphs. Okay, now when we looked at the velocity versus time graphs, we could just pick off a speed, right? At this specific time, I'm traveling this fast. At this specific time, I'm at rest because my velocity is 0 there. At this specific time, I'm going back to the left because I have a negative velocity, which means I'm going back the opposite direction, right? Lots and lots of information at once. Again, the slope meant something. Remember, slope was the change in y over the change in x, y2 minus y1 over x2 minus x1. That's probably what you learned back in Algebra 1. In this case, the y value is the velocity, so that would be the change in the velocity over the change in time. And you may remember that that, by definition, is the acceleration. So the slope of our velocity versus time graph was acceleration, right? How is our velocity changing over time? Now, we also were able to get something else from this, okay? Now, the other thing that we were able to get from this is that we were able to look at the area under the graph, okay? Now, when we looked at the area under the graph, essentially what we were doing is we were finding the area of little squares that were in there and adding those squares together. Now, how do you get the area of a square or a rectangle? Well, it's length times height, or length times width, right? So if my length is in time, so area equals length times width. So if my length was in time and my height was in speed, what do I get when I multiply speed by time? And you may not know that, but if we actually go up here, remember up here we said that the velocity was equal to the change in position over the change in time. If I multiply both sides by that delta t, what I get is that the time times the velocity is equal to the displacement, the change in the position. So the area of my velocity versus time graph was t times v, which is the displacement. You can also work that out by looking at the units, right? If you take the velocity, which is in meters per second, and then you multiply by the seconds cancels out, leaving us with units of meters. So therefore, it ends up working out that the area of our graph here, now of course this is not a rectangle, you'd have to break it up into a rectangle and a triangle, and you can figure out what those areas are, but the area was representative of the displacement. So calculating that area could tell me how far I traveled. And that's kind of interesting that we can get other pieces of information from our graph. All right? So what I want to do now is introduce you to two new types of graphs. Okay? And these are connected to some things that we've been doing in class. The first one is force and distance, position, length. All right? Now, we can read from this at a specific position. When I have traveled 1 meter, what is the force on my object? When I've traveled 2 meters, what's the force on my object? I can see that I was pushing with a large force. When I got to a certain position, I started pushing with less force. Maybe I was getting tired. And then, I decided that maybe I needed to turn around and exert a force in the opposite direction. Now, the object is still moving towards the right, but I'm exerting a force in the opposite direction, maybe causing it to slow down during this kind of process. Now, in this situation, hopefully you're thinking, I've seen an equation before that has force and distance in it, right? Do you remember what that was? It was this. The work equals the force times the distance. Now, why is that significant? Well, force is on the y-axis and x is on the x-axis. So this is our y times our x. Remember when we did that over here, when we did the y times the x, that was the area. All right? So if I multiply these two values, that would be representative of the area under the graph. And so in this case, the area under the graph is the work that's being done. All right? Now, what that means is that I can use this graph with a changing force in order to be able to figure out how much work has been done, how much energy has been added into my system. All right? So I could take, let's go ahead and throw some numbers in here just so that we can see what this looks like. So let's say that we started with a force of 10 newtons, and then by the time we got here, let's say that's 6 newtons, and then the time is 1, 2, 3 seconds, 4, 5, 6, 7 seconds. So in the first 7 seconds, how much work was done? Well, we can find the area. Now, that's kind of a weird shape, kind of a stair-step shape. So we're going to break it up into rectangles. I'm going to have this rectangle right here, and I can find the area of that. And then I can have this rectangle right here, and I can find the area of that. Okay, so rectangle 1 has a width of 3 and a height of 10. And so I can go 10 times 3. That'll give me the area of the first rectangle. And then the second one has a width of 1, 2, 3, 4, and a height of 6. So 6 times 4. So when I put those two together, I get 30 plus 24, which equals 54 joules. So that means that my object has gained 54 joules of energy. Now, why is that important? Well, if I know that all of that energy goes to kinetic energy, I can now connect this equal to 1/2 mv squared, and I can figure out the speed of the object, right? That's something that we wouldn't have been able to do before. But this idea of being able to use a graph with some changing forces, lots of information, we can now find other pieces of information. All right? Of course, anything below the axis here would be considered as negative work. All right? So if we kept going, so 8, 9, 10, maybe goes up to 11 seconds there. Okay? And then this looks like maybe it's a little bit more than 6, so let's say that this is 8 newtons. All right? So if I were to find the area of this, I would go 1, 2, 3, 4 seconds times 8, and I would get 32. Because it's below the x-axis, that would be negative 32 joules. So I would gain 54 joules of energy here, and I would lose 32 joules of energy there. And so you could find out the total energy gained or lost in whatever the situation is. All right? Now, again, my hope here is just to kind of introduce you to this idea, and then we'll get a little bit of practice with it when we're in class next time, just so that you can kind of see how this works. I want you to make connections with slope and area and things like that. The slope of this one is not really helpful to us, force over distance. That's not going to be useful for us at this point in time. We may add that in at some point later in the year, but for now, I just want you to recognize that the area of a force distance graph is the amount of work done. Okay? Now, last one here. This is force time. Okay, so it seems very similar to this one. This is the force being exerted over a distance traveled. This one is, as time progresses, what force is being exerted. This is a little bit different, but the same principle will hold, right? Remember that area comes from multiplying these two things together. So if we say area is going to be equal to F times T, does that look familiar? Do you remember what F times T is? Hopefully you remember it's the impulse, or in other words, the change in the momentum, right? So we can use a graph like this to find the impulse or the change in momentum. Let me show you. So we'll just throw some numbers in here, 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons. So 4 Newtons, and then we'll go 1, 2, 3, 4, 5, 6, 7 seconds. Okay, so this one matches up with that guy. This one matches up with that guy right there. And so by finding the area of this, we can find the change in the momentum. So I've got a triangle here. So the area of a triangle is 1/2 base times height. So I'm going to go 1/2. The base is 2 there, and then the height is 4 newtons. So that would be that triangle. Then I've got this rectangle right here. Okay, the rectangle goes 3 on its base times a height of 4. And then we do have one last triangle over here on the right-hand side, which again will be 1/2 times the base, which is 2, times the height, which is 4. And if we do the mathematics here, we would get 1/2 of 2 times 4, that's 4, plus 12, plus another 4 there, and we end up getting 20. Now this is force times time, which would be Newton seconds, if you want to write it that way. If you don't remember, this is the value for the change in momentum, right, which we mentioned there, the change in momentum, the impulse. So if you'd rather use kilogram meters per second, that's also an appropriate unit. So you can use Newton seconds, that's fine. But if you'd rather use the kilogram meters per second to remind yourself that that's the change in momentum, you can do that. So with that information, if I knew, for example, that the object started at rest, the change in momentum would represent how much momentum it has now. And if I know its mass, I should be able to find out how fast it's traveling. So again, we can use this in conjunction with the other things that we've done so far this year in order to be able to understand more information about the things that we're looking at. Okay? So, again, 2 new types of graphs. The principles follow with some of the things that we learned before. We're not really using slope very much here, but the area is very significant. The areas match up with 2 of those equations that we've learned previously this year, and so we can use that to help us get information that we would not have had otherwise. Okay? Hopefully that makes sense. We will practice this next class, but make sure that you have a general idea of those principles and that you're able to use them when you come into class next time. See you then.